So if you go with the authentication header, which provides only the authentication of the datagram, and if the original IP packet is looking like this, so it is carrying the TCP segment or TCP data in it, and you got the TCP header, right? So the protocol, the IP version 4 protocol is actually carrying this number 6. So meaning it's actually pointing to the TCP header. Next is below this IP header, there is a TCP header. And if you use the transport mode, a new header that I was referring to is actually coming and sitting in between these two headers, the outer IPv header and then the TCP header. That is what this header. And there are some minor changes that are done to the outer header, which is actually the protocol field. So protocol field, now this is what happened, right? The original IP header is here, and the new header is here, and then the TCP header is here. So the original IP header is pointing to this header, and this header is actually pointing to the TCP header. So the protocol field in the outer original IP packet header is replaced, 6 is replaced with the number 51. 51 indicates there is an authentication header that is followed. So that is the number that is associated with the authentication header. And this header, the new network header, is actually carrying the number 6. So number 6 from the original header shifted to this authentication header, and the rest of the things are actually same. So this data from here to here, whatever is there, is actually as it is. So this you take, and then over this you want to provide the authentication. How do you actually provide the authentication? You pass on this entire bunch of the data to a hashing algorithm, and then you calculate the hash and send it along with the packet. So what all is authenticated, including from here to here, whatever is there, including the new header that is added, everything is taken, and then on that you calculate the hash and send it to the recipient. So how exactly? So some of the fields inside the IP packet, as the packet moves from one hop to the another hop, some of these fields get changed, particularly the TTL value that is here. So if let's say original TTL value is 32, if the packet crosses one, so let's say the sender is here and the recipient is here, and then you got 3 routers in between this one. So if the original packet is carrying the TTL value 32, when this crosses this router, the TTL value becomes 31, and when it crosses this router, this becomes 30, and then when this crosses this router, this becomes 29. So as long every hop it crosses, the TTL value decrements, and at the same time the checksum value that is there in the header, the TTL value changes, the checksum value also gets modified, because you change something in the header, and then every router has to recalculate that checksum and then keep updating it. What is the new checksum value? What is the new checksum value? So the checksum values and TTL values are the two prominent elements within the IP header, which actually keep modifying at every hop in the transmission. So when you calculate, when I say that the entire IP packet, whatever original IP packet was there, plus whatever is added, entire thing is actually authenticated. So how do you actually authenticate? You omit these fields which are susceptible for changes during the transmission, particularly these TTL and the checksum value. These are called mutable fields inside the IP header. You omit them and then calculate the checksum and send it to the recipient. So that is how you exactly authenticate. So this is the structure. What happens if you use the transport mode? So a new header is coming in, sitting inside the original IP header and the TCP header. So on the other hand, if you use the tunnel mode, the original IP packet from here to here, whatever is there, so that is as it is intact, and when you create a new IP header, which is this IPv header, and then you attach, additionally you add another header called as the authentication header, and some changes are done inside these headers. So the outer IPv for the new IP header that you added is set, the protocol field in that one is set to 51, and 51 points to this authentication header, and this authentication header inside this, the protocol field within this authentication header actually points to this original IPv header that is identified by number 4. So the next header that you are getting is 51 indicates that the next header is the authentication header, and 4 in this field is actually telling that the next header is another IP header, and the number 6 here is telling that the next header is the TCP header. So that is how it is actually interpreted. And you take everything from here to here, of course again omitting those mutable fields. You calculate the hash value or the message authentication code, and then transmit it or the along with this packet, and the recipient will be able to verify that. So this is what how the structure look like if you use the IP version 4 packet, and then the only the authentication header, not the ESP, in both the modes, IP transport mode and the tunnel mode. So this authentication header, what I was referring to here, has got this kind of the structure. So the fields within that authentication header, this and this, has got these many fields. So from here to here, this is actually 32 bits or 4 bytes. So it has got a next header field. Next header is then identified by that number. So this you can think of it as a protocol number. Number 4 in the previous case was the next header, and then it is indicating the total payload length, because the payload itself can vary. It can be 0 byte, it can be 10 bytes, it can be 100 bytes, whatever it is depending on. So what kind of mode you are operating in. And then so these two are 1 byte entities, and then another 16 bits are reserved. So from here to here you don't use set to 0, and then it carries something called security parameter index. This is the 32-bit string, and this identifies some things. So when I just to recollect your memory, I said that when the two entities begin to communicate with each other, they negotiate what kind of the cryptographic algorithms to be used and as algorithm to be used, and till the connection is actually closed, this connection I need to use so and so encryption method, I'm sending to so and so destination and so forth. These are all identified by this security parameter index. So you can, for the time being, you can think of, depending upon who is the recipient, who is the sender, and what cryptographic algorithms I should be using. So that is identified by this security parameter index. And then there is a 32-bit sequence number. This sequence number is the one which actually uniquely identifies the IP packet. So remember, the original IP packet, IP is connectionless service, and if I send one IP packet here, and then there is no guarantee that this packet is actually indeed received by the recipient. So the P1 is sent from the source, and the router R1 forwards it, and at router R2, for some reason the same IP packet P1 might be dropped. It may not reach the recipient. Then how do the recipient know that so and so packet was sent from the source and it is not actually received by the recipient? Or what is the number, so and so packets have been received and so packets are still missing, they didn't arrive. In order for the recipient to understand or the receiver to know that this is not a duplicate transmission or the something is missing in the transmission, so that is identified by this sequence number. This sequence number has nothing to do with the TCP sequence number. This is actually a number which is linearly incrementing for every packet that is sent. So in the forward direction, whatever you are sending to sender, you number those IP packets as 1, 2, 3, 4, something like that, and then send it to the recipient. And so once you hit, so this is a 32-bit number. So what is the maximum number of the sequence that you can have? 2 to the power of 32 is the maximum number of the packets that you can uniquely identify. So now if I want to transmit more than 2 to 32 packets, then what do you do? So you need to recycle them. So you start with the 0 or 1 and then 2, 3 and so forth. When you hit 2 to the power 32, then the sequence number has to be reset to 0 and then it has to again start. So now how does the recipient know? Since the IP is connectionless, so this recycling of the sequence number within the IPSec header is actually, if a packet is originally delayed or it's dropped and you recycle the sequence number and then retransmit it, transmit it, by that time the recipient will not be able to differentiate whether this is a delayed old IP packet which has arrived or it has the new IP packet which the sender has sent recently after recycling the sequence number. That differentiation not there. What I'm trying to tell is, if let's say sequence number packet with sequence number 10 is lost during the transmission and the maximum sequence number is 100, after 100 you come back to 0 and then start 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This 10th packet at the recipient is actually a new one or the a old transmission which is actually arriving at the at a later point of time. So that recipient is actually not able to differentiate. So there is a method with which such differentiation can be done. We'll see that in the other method that is used for authentication, which is the ESP encapsulating security payload. So the structure look like something like this. So you have an IP packet, original IP packet, and if you use the ESP method, there are two entities that get added. One is the ESP header, and then there is a second entity called as the ESP trailer, and to this you append something called as the authentication data. This is what the hash value or the MAC that we are into. So you attach this. So in the transport mode, you retain the original IP header as it is and then insert this new header between and the protocol field in the IP header is modified. In the previous case it was 51, now it is 50. So 50 identifies it is an ESP header, not the 51 is for authentication header and 50 is for the ESP header. But the trailer is actually pointing to the TCP header. And then you add this hash value or the MAC value at the end. From here to here, including the trailer, ESP, you require both confidentiality and integrity. You encrypt the data, and from excluding this header, from here to ESP header to this place, you calculate your hash value and these two fields from here to here. So this is what happens in the transport mode. So on the other hand, if you use the tunnel mode, the new IP header is here, and as usual, the protocol field in this one is set to number 50 that identifies the ESP header, and then you attach a trailer. So we'll see in a minute what exactly is there in the trailer, and within that trailer, the next header field within the trailer is actually pointing to the original IP version 4 header, and then that is actually indeed pointing to the TCP header, original TCP header. So from the original IP packet from here to here, including the trailer, is encrypted, and the ESP header and the original IP packet plus the trailer is the one on which the hash is actually generated or the calculated, and that is attached to the end of this. So this is what happens in the, if you operate ESP in the tunnel mode, a new header and the new ESP, new IPv4 header, then a new ESP header, and then a trailer, and then the authentication data. So these four quantities are actually added in the tunnel mode. So if you look at the encapsulating security payload, the security parameter index is the same bit string as was there in the previous case, and then the 32-bit sequence number. Again, this is all 32-bit from here to here, and then you got the data. This data is actually this IP original input from here to here. Everything is the data from the original IP packet, whatever is there, including the TCP segment. Everything is data, and to that, some of the fields which were there previously in the header are shifted to the trailer. So what are the three quantities that get added? One is the padding. So this padding is required because we are using an encryption algorithm. So some of the block ciphers requires the data to be of multiple of certain length. If the original IP packet does not contain the data in the multiple of that, so you add that padding and make it multiple. That one. Then you identify that pad length, how many bytes are actually added to that, and then you have got the next header. This is where the header in the trailer, this portion is the trailer, and these two are in the ESP header, and this is the original IP packet. So and then to that you attach something called integrity check value. Integrity check value is nothing but this ESP authentication data. So that's how the things look like. So said entire IP packet is taken, and then it is not multiple of certain length that the cipher algorithm wants. Then you add the padding, and then you identify how many bytes you added, and then you identify which is the following header, and then finally the authentication data. So with that in mind, so both the authentication header and the ESP modes can operate in transport in the tunnel mode. Let's take a look at what are the specific components of the IPSec that are involved. So is required, there are only two things. One is the encryption algorithm that required is the source, and the sender and the recipient or the two communication endpoints can negotiate. I want to use so and so algorithm, and the second one is the hashing algorithm or MAC generation algorithm. Again, the two endpoints can actually negotiate this. And in order to maintain the connectivity, they established something called as the security association between the source and the recipient, or the sender and the recipient, or the in both way bi-directional communication. You establish the security association. Security association defines what kind of the cryptographic algorithm or hash algorithm to be used, and then you got the key exchange method. So these two, source and destination, or the two communication endpoints, have to agree upon, I want to use so and so algorithm, and if they required, we will exchange, generate a new session key, and then we will use it for this particular session or the security association. So there is something, the security association itself, security association is between the two communication endpoints, whether it is the two end system or the two middle boxes sitting in between the two endpoints, which is actually doing this encryption and the authentication, is dictated by two databases that the IPSec uses. One is called the Security Association database, and the second one is the security policy. Together, these two dictate or identify what kind of the security mechanism to be applied, what keys to be used for encrypting, which algorithm to be used for encrypting this particular topic. So let's assume the middle box is the one which is actually doing this IPSec operation. If some end host here or some user sends a particular IP packet, the security policy tells that what to do with this particular packet. So what to do with particular packet means, one thing is, it might say that, policy might say that you don't do anything with this packet. This packet does not require any encryption or anything IPSec to be used. So you just transmit it as it is, plain text, plain IP packet as it is. That is one thing. Or it might say that this is going to so and so particular host, and you need to encrypt using this particular algorithm and using this particular key. That is one thing. So that specification is in this maintained in this database called as the policy database. It identifies a particular security association. Security association has got the details of the security, the cipher suit that is to be used. And normally these are the quantities, the what is the peer IP address, what is the local IP address, who is the sender, who is the recipient, which application layer protocol or the higher layer, whether it is a TCP or UDP which is giving you the data, and then sometimes even the port numbers together can define a policy. So that policy can be particular to one pair of the systems, from here to there, one local IP address and to particular destination IP address, or to every IP address that the sender has got and every IP address at the other end, or on a subset of the IP address. So from this range to this range, if the source IP address is from this range to this range, and if the destination IP address is from this range to this range, you use this security association. Or it can be a wildcard entry, irrespective of what is the source IP address. If the packet is having so and so destination address, this is what you need to use. So it can be all sort of combinations: two wildcards, one wildcard, or one subset, range of the IP addresses at the source level, range of the IP address in the destination field, or the higher layer protocols, the port numbers together actually dictate this policy. And the security association database also contains more or less the similar things. So particular, and then destination IP address, and then the protocol identified field. So these three quantities, whenever a packet arrives at the, you consult the policy database. It will tell you need to do this. Then go and look into the security association database, pick up the security parameter index, and that will tell you which algorithms to be used. Use that, and then do either encryption or authentication, or both of them, and then send the packet. So this is exactly what happens. So these two document databases are of importance for every communication. So this security policy is not only applicable for the IP packet transmission, whether you use the authentication header or ESP mode, and sometimes even if you want to exchange the key. So the I key stands for internet key exchange. So even if you want to exchange a key, how the two endpoints or the two middle boxes are going to derive a new key or exchange a key, for that also the security policy is applicable, depending upon which source and which destination, those combination that we are referring. So the next question in the you ask is, how exactly this association between the two parties are established. One simple technique is you do it manually. So meaning somebody has to go there, and this is the middle box. This is where the encryption happens. This is where the decryption happens, or the other way around. I'm going to configure that. So the key need to be entered, the cipher should, that algorithm that I'm using, which mode, whether it is the transport mode or the tunnel mode, I need to tell explicitly, go and configure it. That is one way. The second is use this automated method, which is the internet key exchange. So internet key exchange method, if you use this, then it will transparently handle all of these things. So there is a kind of thing how exactly you exchange derive the key and exchange between these two parties is there. Without going into the details of that, but you understand this much. So the two parties are there, and they are going to use, if you use IKE, and then automatically the key would be derived, and then it is shared between these two and systems. So to end the discussion, let's take a look at what exactly happens if a packet arrives at a point where the IPSec is actually implemented. So this is an outbound packet. Either TCP or UDP protocol at the higher layer gives a packet, and you consult this policy database in the first place. So if the policy database does not have an entry for this particular pair combination, source and destination IP address pair, then you discard the packet. So just to IPSec encryption or authentication, then also you need to tell that you don't encrypt this packet or don't add any IPSec features into this packet, just transmit it. So at least you need to tell that. In the absence of that, this packet has to go in the as it is without any modification. In that case, you discard the packet. It is not even telling that, you just forward the packet as it is. If there is an entry in that policy document, and if the policy says you bypass the IP security, don't do any encryption or authentication, then you forward the packet as it is. On the other hand, if the policy says you need to protect this packet, either with the authentication header or with the ESP header and the trailer. So you search, identify what is the security association relevant to this particular combination of the source and destination IP addresses and the protocol fields, and then you add accordingly whatever the relevant headers, either the authentication header or the ESP header and the trailer, or whether it is operating in the transport mode or the tunnel mode, you add that header and then forward the packet. If the security association, the existing association, security association has expired for some reason, but the packet still has to be processed for thing, then you consult this internet key exchange automatic key distribution mechanism, and then establish a new security association. So in fact, what the IPSec does is, when the sequence number field, you start with 0, 1, and when you hit 2 to the power of 32, the security association, the existing security association is terminated. And you need to, these two endpoints or the middle boxes have to generate a new security association. So in that case, that might be one of the reason you consult this key exchange protocol, and then you derive or establish a new security association for these endpoints. Then you start with the sequence number 0 and then continue on to until 2 to the power of 32. So this is a very simple operation. So if you find an entry in the policy document, if it is bypassed, just without doing any modification, send the IP packet. If it is saying you need to do some IPSec related processing, then identify the security association field, consulting that database, add either the authentication header or the ESP header. If that as security association is expired, you re-establish the security association, then process it. If there is no policy relevant to this particular IP packet, you just discard that IP packet. The companion operation happens more or less, the reverse operation happens at the other end. You receive a packet, and again you consult whether the policy document. If the packet is plain IP packet, packet, and if it is saying that for this particular packet you need to bypass the IPSec, then you deliver it to the upper layer. And if it is not bypass, this particular packet is not supposed to come in the plain IP format, and if it has come, then you discard that packet. And if that is the packet has to be identified as the packet is identified as the IPSec packet, then you search the relevant security association and then you process it accordingly, whatever it is saying, either using AH or ESP related to header and the trailers operating in the either transport or the tunnel mode, and then deliver it to the upper layer. So that is what happens at the recipient end. So just to summarize, IPSec provides the security, the confidentiality, integrity, and the data origin authentication at the network layers. So it can take the data from both the TCP or the UDP packet and then establish a tunnel between two communicating endpoints. So the actual implementation can be at the end host itself, or some middle boxes sitting in between these two conversations can actually do the or establish the tunnel and then transfer the data. And the IPSec itself provides two kinds of the operations. One is only the authentication, second one is the encapsulation, which comes with the authentication plus the encryption, and these two can operate in a transport mode or a tunnel mode. In the transport mode, the original IP header is kept as it is with slides with some modifications. In the tunnel mode, you take out the original IP packet and encapsulate in a newer IP outer IP covering and then transfer it. And any security algorithm that are used for encrypting or for a particular tunnel conversation is actually identified by something called a security association, and this security association dictates what kind of the algorithm to be used and